Welcome back to the Deep Dive. Today we're plunging into the fascinating and, well, pretty extreme world of Wolf-Rayet stars.
Yes, and we've got some really interesting source material here. It's from Michael Perryman's text on Gaia science, and it specifically zooms in on these stellar behemoths.
Right, so our mission for this deep dive, essentially, is to unpack what these stars are, why they're so significant, maybe why they've been so challenging to study.
And crucially, how data from the Gaia mission, this incredible precision data, is really changing our whole picture of them.
Yeah, think of this as your way to get quickly up to speed on a really captivating topic. We're
Right.
digging into the key stuff from the material, so let's just jump in. What exactly is a Wolf-Rayet star?
Okay, right. So basically, a Wolf-Rayet star represents this really dramatic final phase. It's when a really massive star is burning helium in its core.
And massive means.
We're talking stars that start out as O-type stars, initially more than about 25 times the mass of our sun, big ones.
Okay, proper giants then.
Yeah.
And they have a sort of signature look, right, in their spectra.
They absolutely do. That's actually how they were first spotted. Back in 1867, two astronomers in Paris, Wolf and Rayet, hence the name.
Oh, makes sense.
Yeah, they noticed these stars had these really peculiar spectra, very prominent broad emission lines, especially helium lines.
And the broadening. That tells us something important.
It does. It's Doppler broadening. So the Doppler effect tells us stuff is moving, right? In this case, the broad lines mean gas moving at really high speeds away from and towards us.
So that's the stellar wind signature.
Exactly. It points to these incredibly dense, incredibly fast stellar winds they have.
Wow. So it's not just what's happening inside, but this massive outflow. And does that outflow sort of reveal different layers as the star evolves?
Precisely. These winds are so strong they strip away the outer hydrogen layers first. And when they do, they uncover material that's been processed by the CNO fusion cycle deeper inside.
Okay, the carbon, nitrogen, oxygen cycle.
Right, so that material's rich in nitrogen. We call those WN stars. Then later, the winds peel back even further, revealing a deeper layer where helium burning has cooked up lots of carbon and oxygen.
And those are the WC and WO types.
You got it. WC and the even more evolved WO types.
So it's like they're shedding their skin and showing us their history, layer by layer, as they get near the end.
That's a great way to put it. And speaking of the end, this Wolf-Rayet phase, it doesn't actually last very long, cosmically speaking. It's a pretty brief period right at the end of core helium burning.
And after that?
Well, once that helium fuel runs out, bang! Usually supernova explosion expels even more material and the core collapses.
Into a neutron star or a black hole?
Probably a black hole, given how massive these stars start out, which really makes this Wolf-Rayet phase super significant. It's likely the very last stage we can actually see before that final, collapse.
Okay, but you mentioned these incredibly dense winds. They must sort of hide the star's actual surface, right? How well do we actually know their basic properties, like temperature or size?
Yeah, that's definitely a challenge. The winds are optically thick, meaning you can't see right through them to the stellar surface. But based on models and looking closely at their light and spectra, we can get pretty good estimates.
Okay, so what are we talking?
We're talking incredibly hot, effective temperatures, somewhere between 30,000 Kelvin up to maybe 150,000 Kelvin. Just scorching.
In size-wise?
Relatively compact for how massive they are, maybe 1 to 15 times the sun's radius. But their brightness, their luminosity, that's enormous.
Oh, enormous.
Like 100,000 to 1,000,000 times the luminosity of our sun, just pouring out energy.
Unbelievable. And the mass loss, you said that was extreme, too.
Oh, it's legendary. They're shedding mass at rates like 10 to 4 solar masses every single year.
Just put that in perspective for us.
Okay, well, think about it. Our sun has lost only a tiny fraction of its mass over billions of years. A Wolf-Rayet star can lose the sun's entire mass in just like 10,000 years, maybe a bit more or less, depending on the rate.
That's steep.
It really is. And this material isn't just, gently drifting away. It's blasted outwards. Terminal velocities of like 1,000 up to 3,000 kilometers per second.
Just incredible speeds. So even though they have these really distinctive spectra that let astronomers spot them from far away, the source material says they're actually pretty rare.
They are indeed very rare. In our whole Milky Way galaxy, the estimate is maybe only around 1,200 of them total.
Wow. Out of hundreds of billions of stars.
Exactly. It's a tiny fraction. And right now, we've actually cataloged just over 800.
Has that number grown over time?
Oh, yeah, definitely. As surveys get deeper, an older catalog, back in 2006, only listed about 298.
So quite a jump.
A big jump. And even in really dense places, like the massive star cluster Westerlin 1, back then they only knew of 24. Near the galactic center, maybe 60 or so.
What about in our galactic neighbors, like the Magellanic Clouds?
We find them there too, but again, small numbers. The Large Magellanic Cloud, the LMC, has around 150 known. You might see them designated B1899, or sometimes Radcliffe R numbers. Like R136A1, that famous really massive star, is in a cluster of them.
Right, I sure thought that.
And the Small Magellanic Cloud, the SMC, has even fewer. The material mentions about 12 with AB designations.
So not many, but they are around. Is
Yeah.
one particular type more common?
Yes, among the ones we know, the majority are the WN subtype, those ones showing the nitrogen enrichment first.
Okay, so they're rare, but the sources really emphasize they have this huge influence on their surroundings, right? They punch above their weight.
Absolutely. Despite being few in number, their extreme nature gives them a massive environmental impact. I mean, first, those incredibly high temperatures, they produce just vast numbers of high-energy photons.
Which does what?
Ionizes gas. They can light up huge clouds of hydrogen gas around them, creating bright nebulae, shaping whole star-forming regions. But maybe even more important is that mass loss we talked about.
All that material being blown out.
Exactly. It's not just hydrogen and helium. It's loaded with heavier elements, what astronomers call metals. Carbon, nitrogen, oxygen, produced inside the star and now getting ejected.
So they're enriching the galaxy?
Deeply enriching the interstellar medium, yeah. Seeding the gas clouds with the building blocks for the next generation of stars, planets, maybe even life. So even in their short, violent final act, they're crucial for cosmic chemistry. However, and this is a really big however, despite how distinct and important they are, these final stages of massive star evolution are, well, still surprisingly poorly understood.
Really? What are the main things we still don't quite get?
There are quite a few major gaps, big uncertainties in exactly how much mass they lose and how that process works during the Wolf-Rayet phase itself, how much angular momentum they shed, how material gets mixed around inside the star.
Okay.
And then there's a really critical factor, binaries.
Binary stars.
Yeah.
Two stars orbiting each other. Why is that so key here?
It's potentially huge. Because we know massive stars often form in pairs or multiples, and their interactions can just completely change how they evolve. We need to know, like, what fraction of Wolf-Rayet stars are actually in binaries?
Right.
How does being close enough for one star to dump mass onto the other change things? What happens if one swells up and engulfs its partner, this common envelope phase? Or what if they just straight up merge?
Wow, okay. So whether they evolve alone or with a partner could lead to totally different outcomes.
Fundamentally different paths to becoming a Wolf-Rayet star, and maybe even different kinds of supernovae. And the source material points out all these things, the mass loss, the mixing, the binary effects, they likely depend on the star's initial metallicity, the amount of heavy elements it started with.
It's complicated.
Very. And figuring out the impact of all these factors is really important, not just for Wolf-Rayet stars themselves, but for understanding galaxy evolution, supernova types, gravitational wave sources, lots of stuff.
And this leads us to something absolutely fundamental for stellar astrophysics, knowing the distance. You can't figure out how truly bright a star is, its intrinsic luminosity, unless you know precisely how far away it is.
Exactly. Luminosity is key to everything else, mass estimates, mass loss rates. And the problem was, for most Wolf-Rayet stars in our galaxy, the distances were just not well known. Poorly constrained before we had dedicated space missions.
We did get some earlier space data, though. Didn't the Hipparcos satellite try measuring some parallaxes back in the 90s?
It did, yeah. Hipparcos observed about 67 galactic Wolf-Rayet stars, pretty much all the ones brighter than about magnitude 12. And that data was definitely useful.
Like for what?
Well, one example mentioned is a study looking at runaway stars, stars moving unusually fast. They used Hipparcos data and found it kind of supported the idea that these runaways got kicked out of the clusters where they were born.
Okay. And there was one really specific bright star mentioned, Gamma Velorum.
Yes, a Velorum, or WR11. It's actually a multiple system, but the Wolf-Rayet component makes it the brightest and nearest one we know. Hipparcos got a pretty good parallax for it.
And that gave a distance of?
About 258 parsecs, plus or minus a bit.
And that was different from before?
Significantly different. Previous estimates, even ones thought to be rather secure, put it much further, like 450, 460 parsecs.
Wow. So what did that change?
Well, the closer Hipparcos distance actually helped solve a puzzle about its mass loss rate, which seemed too low for the old distance based on radio data. It fit much better closer up. But it also meant Jovelito probably wasn't part of the nearby Vela OB2 association anymore, so it kind of shifted its context.
So one accurate distance measurement ripples outwards.
Exactly. It shows the power of precise astrometry. Interestingly, Avalella is so bright, it's actually one of the very few really bright stars that doesn't have a standard Gaia parallax yet in the main data releases, just because processing such bright stars is tricky for the instruments.
Okay, so if Hipparcos already made a difference, Gaia, with its precision for, what, billions of stars, must be completely changing the game for Wolf-Rayet stars.
Oh, absolutely. Gaia is revolutionizing stellar astrophysics across the board, and this field is definitely feeling it. The source material makes it clear. Gaia data is having a really significant impact on how we model Wolf-Rayet evolution going forward. You're already seeing papers coming out using Gaia data to update what we know about specific stars or whole groups.
And the sources specifically pull out two papers that use the second Gaia data release, DR2, right? To look again at the basic properties of the main Wolf-Rayet types, the WCWO stars and the WN stars.
Yeah, this is where Gaia's distances really let astronomers pin down those intrinsic luminosities properly. Maybe just a quick reminder on the subtypes first.
Good idea.
So WCWO stars run from WC4 up to the WO types. WN stars go from WN2 up to W11. And often they're grouped into early, the hotter ones, WCE, WNE, and late, the cooler ones, WCL, WNL.
And you mentioned something about hydrogen earlier.
Right. Generally, the early WN types, the WNEs, are thought to be pretty much hydrogen-free. They've lost that outer envelope. The later, cooler WNL types often do still show hydrogen lines.
Meaning they haven't shed everything yet.
Exactly. And crucially, the thinking was that these early and late types had quite different physical properties, like luminosity.
Okay, so let's take the WCWO stars first. The Sander et al. Paper from 2019 used Gaia DR2 for those. What did they find?
Right. They looked at 56 galactic WC stars and 3 WO stars with these new distances, and they found something. Well, pretty surprising, actually, based on what people assumed before.
Oh, what was the surprise?
They discovered that WC stars classified as the exact same spectral subtype, so they look spectroscopically very similar, could actually have significantly different intrinsic brightnesses. Different absolute magnitudes, different luminosities.
How different?
The range they found using the Gaia distances was from log LA of about 4.9 up to 6.0.
Okay, what does that translate to? Like 4.9 to 6.0?
That difference, 1.1 in the log, means the brightest ones in that group are more than 12 times more luminous than the faintest ones.
Wow. Even though they're the same spectral type.
Exactly. That really flew in the face of the assumption that stars of the same subtype should be much more uniform in luminosity.
So a WC5 isn't just a WC5. They can be fundamentally different beasts in terms of power output. What does that imply?
Well, the main implication is that these WC stars probably form from a wider range of initial masses than previously thought. Maybe stars that start out quite different end up looking spectroscopically similar during this phase.
Okay.
They found similar things for the WO stars, too. And it suggests we might need a kind of complete overhaul of the spectral analysis, probably needing new atmosphere models to figure out what's really going on.
And since luminosity affects how you calculate mass loss from spectra,
Yeah.
those rates need revising too.
That's right. If the luminosities are different, the derived mass loss rates change too. So Sander et al.'s conclusion was basically, okay, we still think these are evolved, core helium-burning stars, sure, but the details of how they get there, much more uncertain now than we thought.
Okay, so Gaia reveals unexpected diversity among the WCWO stars. What about the WN types? That was the Haman et al. 2019 paper.
Yep, similar approach. They used Gaia DR2 distances for 55 single WN stars in the galaxy. And again, for many of these, previous distance estimates were pretty shaky.
How did the new Gaia distances compare? Were they way off?
On average, maybe about 10% smaller than older studies, which isn't dramatic. But in some extreme cases, the difference in distance modulus was up to minus 2.6 magnitudes.
Minus 2.6 magnitudes. What does that mean in distance terms?
It means the star could be more than 3 times closer than previously thought based on that old estimate. Or further if the sign was the other way. That kind of error directly messes up your luminosity calculation.
Massively. So with these better distances, what did they learn about WN stars?
Well, when they looked at things like how mass loss rate correlates with luminosity, they found a lot more scatter than expected. The relationship wasn't as clean or simple, and the slopes of those correlations were also shallower than previously found.
Okay. And where do they sit on the HR diagram, that temperature luminosity plot?
The general picture held up. The hydrogen-free early types, WNE, are mostly on the hot side of the zero-age main sequence where stars start hydrogen burning. The late types, WNL, often with hydrogen, are mostly at cooler temperatures, sort of cooler than the Zamaskis.
Yes. I sense a but coming. Did the Gaia data show anything unexpected there?
Yes. This is the real curveball from Gaia. The distribution of luminosities for WN stars seems more continuous than people thought. It's still generally true that the late WNLs are typically brighter than the early WNEs, but there's a significant overlap in luminosity.
An overlap, meaning?
Meaning in a specific range, roughly log LA between 5.5 and 6.1, you find both early hydrogen-free WNE stars and late hydrogen-showing WNL stars.
Wait, okay. So you can have a hot star with no hydrogen and a cooler star that still has hydrogen, but they have basically the same intrinsic brightness.
Exactly. That was not the standard picture. And here's the kicker, highlighted in the source. Based on this new Gaia data, neither the latest single-star evolution models nor the current binary evolution scenarios could fully explain the range of properties and where these stars sit on the HR diagram.
Whoa. So Gaia isn't just tweaking numbers. It's actually saying our fundamental models might be missing something important about how these stars evolved.
That's exactly it. It's the power of precise data forcing us to reevaluate the theory. Where are our models or simulations incomplete?
Okay, so beyond the basic physics, Gaia is also helping revisit where these stars are and how they got there, right?
Oh.
Like the runaway star idea we mentioned.
Right. Another paper, Rate and Crowther from 2020, used DR2 distances for nearly 400 galactic WR stars. They combined that with info on HII region's good tracers of where massive stars form to see who strayed far from home.
Did they find runaways?
They identified 31 stars that are significantly far above or below the galactic plane, more than 156 parsecs away, as potential runaways.
Is that what previous studies expected?
Well, the source notes a contrast. Only 4 of these potential runaways they found are WN89 subtypes. Older studies might have suggested a larger fraction of those specific types would be high-velocity runaways, so maybe a slight adjustment to that picture.
And what about cluster membership? Are most of these stars still living in the clusters where they were born, or are they mostly loners?
Good question. Another Rated All paper from 2020 tackled that, using Gaia DR2 parallaxes and proper motions how they move across the sky. They looked at over 500 WR stars away from the galactic center.
To see if they belong to known clusters or associations.
Exactly, and the result was pretty striking.
What did they find?
They found that only somewhere between 18% and maybe 36% of these Wolf-Rayet stars are actually located in known clusters or OB associations.
Okay, hang on. So flipping that.
It means at least 64%, potentially more like 80%, of the known Wolf-Rayet stars in the disk seem to be isolated. They're not currently linked to a birth cluster.
That's a huge fraction. That really suggests that either many of them are born outside clusters or they get ejected very effectively or the clusters dissolve.
Yeah.
It changes how we think about their environment.
It certainly raises questions and, putting it all together, the revised luminosities, the wider mass ranges, the unexpected overlap between WN subtypes, the fact that our models are struggling, and this high fraction of isolated stars.
Yeah.
It all points back to the main conclusion from the source material. Gaia's data is having this really profound ongoing impact. It's forcing us to rethink many aspects of this really crucial final stage of massive star evolution.
Okay, let's quickly recap what we've covered from the Perryman source material. We learned Wolf-Rayet stars are this dramatic end phase for really massive stars, burning helium, shedding mass like crazy through these powerful winds.
Right, winds that give them distinct spectra, but also hide the surface. They're rare, but have a huge impact, enriching the galaxy with heavy elements.
But understanding them has been tough. Lots of uncertainties about mass loss, internal mixing, and especially the role of binary partners.
And then came Gaia. Its precise distance measurements are the key. They let astronomers revisit fundamental properties like luminosity.
And finding surprising results, like WC stars of the same type having very different brightnesses, implying wider initial masses.
And WN stars showing this unexpected overlap in luminosity between early and late types, which current models, both single and binary, can't quite explain yet.
Plus, Gaia showing that a huge majority, maybe 64% or more, seem to be isolated, not in clusters.
Yeah, it all points to a more complex and perhaps diverse set of evolutionary paths than we previously appreciated.
So, here's something to think about. Considering how many of these Wolf-Rayet stars seem to be loners, and how our current models are really struggling to explain the properties Gaia is revealing, what does this suggest about the sheer variety of ways massive stars might live their lives and reach their explosive end as supernovae, ultimately leaving behind neutron stars or black holes. Maybe the paths are more varied than we ever thought.
It certainly seems that way. There's clearly still so much to learn about these incredible objects, and Gaia is giving us the tools to ask much sharper questions.